Huffman coding. Huffman coding is a lossless data compression algorithm which uses greedy technique. Let us first understand what is lossless data compression. So this is mainly used whenever you want to transfer some data. If you want to transfer from point A to point B, what do you have to do? You have to make sure that whatever be the amount of data you are having, it should be as compressed as possible so that you can gain in the cost of transfer. If you are having a lot of data, transferring it completely from one end to the other end would be too much of cost. So if you can compress this data and make it small, then your cost of transfer would be minimal. So this is why you always want compressed data. The next thing is lossless. What is lossless here? Let us understand lossless. Your data that is in English has to be first converted into binary. And then this binary will be transferred from point A to point B. And at point B, you have to convert the binary back to English. So this is the process that you have to follow. In this process, when you want to convert English to binary and then convert binary to English, you should make sure that there is no loss of information. That is what is called as lossless data transfer. When you're converting from English to binary and later decoding this binary back to English, you should be able to regenerate the same data in English that was present at the source. This is what is lossless. So in order to do this, you will use Huffman coding. Huffman coding will help you to encode from English to binary and similarly to decode from binary to English. In this particular lecture, we'll be looking at how do you encode from English to binary so that it is lossless and as compressed as possible. So talking about compression, about the binary code that you can convert and gain, let us understand what should be the properties this binary code should be having. First of all, let us say we are converting each letter into a binary code. So you have letters A, B, C, D, etc. And for each letter, you have to assign a binary code. While assigning, first thing you have to make sure is that it should be a prefix code. What is a prefix code? Prefix code means whatever is the code assigned to one character. Let us say I assigned the code 10 to A. This code should not be the prefix of the code assigned to any other character. What is the problem if it is the prefix? Let us say I assigned code 1 to A, 11 to B, 111 to C, and 1111 to D. The problem is these are prefix codes. That means the code assigned to A1 is a prefix of the code 11. Similarly, code assigned to B, that is 11, that is a prefix of the code 111. So whenever it is a prefix, the problem is that let us say you encode it from English to binary, but then when you decode back from binary to English, let us say I encoded cab, C-A-B. This is what I encoded. So C is 3 ones, 111, A is single one, and B is 2 ones. If I send this to the other side, what happens? He'll receive 6 ones. From this, it is very difficult to decode back what was the actual word because this can also be 6 A's, that is A, that also has the same encoding. Similarly, it can also be 3 B's. If it is B, 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 that will also be 6 ones. So this problem occurs whenever you do encoding using a code which is not prefix code. What is prefix code? Prefix code means you cannot use another code which has the code of any of the already assigned codes as a prefix. So let us try converting this into a code which is not a prefix code. That is, if it is 1, B can be 0, 1. That means if you see the first letter 0, it is not first binary digit 0. It is not the code of any other letter that we wrote till this point. So it is not a prefix code. And one more thing, you call it prefix code or prefix free code. Both are one and the same. It might be a bit surprising to see that two words, prefix code and prefix free code, both mean the same thing. Both means a code which is assigned to a character should not be the prefix of any other code. That is what it means. Both prefix code and prefix free code. You will use both these words interchangeably. Both mean one and the same, be it prefix code or prefix free code. Okay. Then let us say the code for C. It can be something like 001, because then 01 does not occur here. That means it is a prefix code. Let us say D is 0001. In this case, each of your letter has a code which is not the prefix of anything else. This is rule number 1. And what is the rule number 2? Rule number 2 is you should always try to make it as compressed as possible. And this is where Huffman code is very useful. It makes sure the code is prefix code. That is fine. But compressing and keeping the smallest possible code, that is where Huffman code comes in. I'll just show you an example to make you understand how the length of code affects the final message. So if you use simply, let us say you decided that you are going to use codes of the same length. And let us take just two letters. One is A and the other letter is, let us say, Q. For A, you assigned a code which is of 4 bits. Let us say 4 bits. Similarly, for Q also, you assigned a code which is 4 bits. In this case, consider that in your document, A is occurring 100 times and Q is occurring 10 times. If this is the case, just if you consider A and Q, in your total document, 100 times A occurred, which means 100 into 4, 400 bits are used for encoding just the A's in your document. Similarly, when you want to encode all the Q's, each Q takes 4 bits and there are 10 Q's in your document. So it totally takes 40 bits in order to encode all the Q's. So in total, A and B, all the A's and B's, when you complete encoding, you would have used up 440 bits. This is the situation if you use same length code for A as well as Q. Let us make a small change. Instead of using 4 letters for A and Q, I'll make it 3 for A and let us say 5 for Q. If I do this, it may seem interesting here, that is, A is happening 100 times. Considering that its frequency is larger, I tried to use a smaller code for A and I am using a larger code for Q because Q is occurring less times. This time what happens? Instead of 400, A will use up only 300 bits because 100 times 3 bits. And what about Q? Instead of this 40, it will be taking up 50 because 10 times it is taking 5 bits. But this time 300 plus 50, the total is 350, which is much lesser than 440. So this is where using the right encoding, the right number of bits and the right code will help you in making it lossless as well as compressed. So let us see how to find the best possible compressed codes. That is, whatever you get from the Huffman coding, that will be the best possible code that you can assign according to the frequencies of each of the letters. So this is what we are going to do. So what is our problem statement? The problem statement is you are given a set of characters, let us say letters, and along with that you will be given corresponding frequencies. So you are given n characters, something like A, B, C, D and so on. You will also be given the corresponding frequencies of all these. Let us say A is occurring 100 times, B is occurring 150 times, C is occurring 75 times and something like this. These frequencies will also be provided. What do you have to do? You need to find out the binary codes of the character such that there are two conditions. What is the first condition? The first condition is it should be a prefix code or prefix free code, whatever you may say is the same thing. Secondly, what is the second condition? The total cost should always be minimized. What is the total cost? Weighted sum of the code lengths. That is, if you are having, let us say, 4 length code for one letter, that into the number of occurrences of that particular letter plus whatever be the length of the next letter into number of occurrence of that letter, and so on. This is what you call as weighted sum of length. Okay. So this is the problem statement. You are given these letters and their frequencies. You want to find the best fit code such that it is a prefix code and it minimizes the total cost. This is the Huffman coding problem statement. Let us see how we are going to tackle this. How are we going to prepare codes which are the best prefix codes which make lossless data compression possible. So the steps are like this. You understood the problem statement, right? So the steps are, first thing, you have some input. So input is, let us say, characters and frequencies. So some set of characters, A, B, C, D, etc. and their corresponding frequencies, something like 10, 15, 20, 12, something like this. Okay. This is your input. This is your input. What is the next step? Once you got the input, you should create each of these letters, you should create leaf nodes. So what are leaf nodes? Already in the tree lectures, you should be familiar with nodes. So first thing you will do is, each of these letters, you would consider them as leaf nodes. So corresponding to A, corresponding to B, corresponding to C, and corresponding to D, you prepared leaf nodes. And what will be the value of these leaf nodes? The value in these leaf nodes will be the frequency of those letters. So for A, you will give 10, for B, you will give 15, and so on. The frequencies are what you have as values. The third step is, once you have the leaf nodes ready, you should build a priority queue from these leaf nodes. Using all these leaf nodes, you should build a priority queue. What is a priority queue? Priority queue is same as a min heap. So in the heap lectures, we discussed about min heap. Whatever is the min heap, the same is what we are calling as priority queue. If you are not clear about min heap, please go to the heap lectures under data structures playlist. There you will find the heap lecture. Once you're clear with heap, all these concepts will be clear. Otherwise, if you have some random idea about heap, that should be good enough to go forward right now. You can keep continuing. You will build a min heap. So you are building a heap. In this heap, you have all these nodes. So you have A, B, C, D, all these are inserted in heap, something like this. Okay. Once you have this heap, next step is, so till this point it is clear, right? Once you have this heap, next thing is, iteratively you have to follow the following steps. Iteratively following the following steps. First thing, you have to pick 2 of the smallest nodes from this heap. What is the speciality of min heap? Always the smallest node will be on top. Smallest node in the sense in terms of value. Here our value is frequency or number of occurrences of that word. Whatever be that frequency, according to the frequency, whichever node is the smallest, that will be on top in the heap. So for what will you do? You will first extract the smallest node from here. So S1, let it be the smallest. Whichever is the smallest or lowest frequency one, you will pick that and again you will reheapify. When you reheapify, what happens? You picked S1, then you want to reheapify. So when you reheapify, what happens? It will again become a min heap with the remaining nodes. So initially you had 4, now you have 3 nodes. Once you do this, you have to pick one more. We already told you have to pick 2 of the smallest, right? So S2 be the second one, and again you will reheapify. So when you took S2, what happened? You got 2 of the smallest frequency nodes from this heap. Once you get 2 of the smallest frequency nodes, you have to create a new node which is having left child as S1 and right child as S2. And what is the value of this new node? The frequencies of the two child nodes S1 and S2 added up will give the value inside new node. So you are creating a new node which is having frequency equal to frequency of S1 plus frequency of S2. That will be the value inside new node. Okay. This is what you are creating. And once you create this node, what should you do? You should add this new node back into the heap. So at this point, you can have a doubt. That is, in the heap, you are having nodes and each node is having a left child and right child in the heap. Let us say some may not have a left child, some may only have a some may not have a right child, some may only have a left child, but still inside that heap they have left and right childs. And I'm telling you that the newly added node already has a left and right child. Then how can you add it somewhere? So the answer is this heap, that is, the doubt will be what sort of a structure should you design for this? So the answer is heap, you are going to maintain an array for a heap. So if you see a heap lectures, we generally don't go for direct structures and pointers. You'll have structures, but maintaining the heap, that you can do easily from an array. So what can you do? From your array which represents heap, each position can point to one particular node. That is how you are having. So if you want to take one node out, you will be taking one particular node out from this array. That is, it will point to a pointer. So initially it will be a leaf. Once you prepare this new node, that is, which is having left and right children, you only have to take the address of the root, that is, whichever is the newly prepared root which is having S1 and S2, and you just have to enter this particular address into whichever array position you want to. So this is why it is easier to implement here. In the array, you just have to add an address, the address which points to the root node, and that root node is what you have newly created. So once you created this root node, you can easily add this root node into the heap. Once you add it back, what should you do? You should again continue these steps. You should again take the smallest out, then the second smallest out. You should add smallest and second smallest. That is the frequencies of smallest and second smallest. That added value will become the frequency of the new node. And whatever was your smallest node, that is, initially it is a smallest node, maybe at a later stage it may be a smaller subtree. For example, you are inserting this particular subtree back into the heap. So next time, if you are taking this particular node as the smallest, it will not be a single node. Instead, this whole subtree will come out. So that is why you may have a node or a subtree. Whatever it be, you will be adding the frequency of root of left and frequencies of left and right to get the frequency of root. Once you do this, you should keep doing this process iteratively again and again till your min heap is having only one element. If your min heap is having only one element, what does that mean? At that point, all your prefix codes are already ready to be created. Your all work with min heap is completed. The only remaining work is to assign binary codes. And next question is, how are you going to assign the binary codes? So let us see how to assign binary codes. Just assume that the tree that you found is something like this. Okay, here let us say you have A, and here you have B, and let us say here you have C and D. If it is something like this is your tree, how do you assign the codes? Assigning codes is very simple. You simply put zeros and ones. Whichever is the left child, this particular link you will give 0. For the right one you will give 1. For the left you will give 0, right you will give 1. Once you do like this, you have to traverse from the root till whichever letter you want to get, the node corresponding to whichever letter you want to get. It will give you the prefix code corresponding to that letter. For example, if this is the final tree that you got in Huffman coding, If this is your Huffman tree, then A will be represented by 0 because from the root, if you move to A, you have to pass through only one 0. So A is represented by 0. What will B be represented by? B will be 1, 0. So that is how you reach B. It is 1, 0. What about C? C is represented by 1, 1, 0. So C is 1, 1, 0. And D is 1, 1, 1. This is D. So this is the Huffman code. If this is the tree, what we'll do is we'll take an actual example and see step by step how each of the step transforms and how is the final Huffman tree formed. So that will make the whole concept very clear for you. So this is what we are going to do. We'll go through the whole Huffman coding process very clearly. And one more thing, in the greedy algorithms, I told you that whenever you want to write a greedy algorithm, you have to make sure that greedy is suitable for this particular problem. And how do you make sure that greedy is suitable? There are two properties of greedy to be satisfied. What are the two properties? First thing is greedy choice property, and second is the optimal substructure property. What about the greedy choice property here? Is it satisfied? Greedy choice property says your solution, you should always be going for locally optimal choices. And what should it provide you with? If you go for locally optimal choices at each step, finally you should reach global optimum solution. This is what greedy choice property says. So let us see if this is followed in Huffman coding. In the algorithm we had explained, what happened? At each step, you are choosing two of the smallest frequency nodes, and these are selected and merged into a new node. This is what you are doing. Each time you are selecting two nodes which are of the smallest frequencies from the heap, and then you are merging it into a new node. When you do this, it ensures that the lowest frequency nodes are placed as deep as possible in the tree. How is it getting done? Let us say you took two nodes, you prepared one parent node and you put it as left and right child. These are the two of the smallest nodes, that is S1 and S2. When you do this and insert this subtree back into the heap, what happens? Next time when you are again picking this and let us say adding it with any other node, the new node will be coming here and these two will be added to form a new subtree, which means your S1 and S2 are going deeper and deeper in the tree. When it goes deeper, that means its Huffman code will be larger, because in order to reach from root till this S1, you will have to move larger distance, which means two of your smallest frequency letters are getting larger Huffman codes, which is a positive thing. You should have smaller codes for the higher frequency letters and larger codes for the lower frequency letters. So this is getting satisfied when you do this greedy choice. And because of this, if you do this greedy choice, finally you will be reaching the global optimum solution, right? So because of this, greedy choice is satisfied in this particular algorithm. What about the optimal substructure? The optimal substructure property says the optimal solution to the problem that should contain optimal solution to its sub-problems, which means you should be able to break the problem into sub-problems, and the solution to these sub-problems should finally give you the optimal solution to find the main problem. Is that getting done here? Let us just think about this. The optimal tree for a given set of frequencies contains optimal tree for its subsets. That is, if you have let us say this is your final Huffman tree. Okay, this is your final Huffman tree. If this is the optimal final Huffman tree, how did you build it? You built it parts by parts. You took two, then merged it to become one particular subtree, and then you inserted it back into the heap, again took it, again merged it with this part, and then you got the larger subtree. So how it happened is you broke it into smaller problems and you solve the sub problems, because of which the optimal substructure property is also holding here, and you're good to go with greedy strategy. So now that you know greedy strategy can be applied and that greedy algorithm is also known to you, we already learned about the algorithm. Let us have a dry run. Let us take some numbers and letters and try to actually build a Huffman tree. Okay. So when you build a Huffman tree, let us say your letters are A, B, C, D, E and F. These are the letters that you're having. And let your frequencies be 5, 9, 7, 15, 3 and 10. These are the frequencies. What is the aim? We are going to build the Huffman tree for this particular set. First thing you have to do is you have to build a heap. So on this side, I will be building a heap, a min heap. Okay, it is a min heap. It is called either a min heap or a priority queue, because priority queue is generally implemented using min heap only. That is why I'm interchangeably using priority queue or min heap. So what I'll do is, for easy understanding, instead of drawing a complete min heap here, what I'll do is I'll try to put all these in ascending order. So if I put in ascending order, the advantage is you'll clearly see which is having the lowest frequency, which is having the largest frequency. So in min heap, the problem is you'll only see top one is having lowest value and the remaining won't have any particular rule. So because of that, understanding will be difficult. So I'll just put it in ascending order. So you'll clearly see at every stage which are the two smallest values. Okay. So as of now, if we just put this in ascending order, which are the smallest ones? E is having only 3. And what is which is the next smallest? A is having only 5. Then next is C. C is having 7 as the frequency. B is having 9 as the frequency, and F is having 10 as the frequency. D is having 15 as the frequency. This is the present situation. So what we'll do, we'll put frequency on top. Okay, for now, let us keep it like this. From next time, you'll put frequency on top. What should you do first? You have to pick two of the smallest ones from this min heap. So just imagine this is a min heap. I'm putting it in ascending order. Smallest ones are E and A. So initially I took E, which is having a frequency of 3. And so I already told you all these are separate leaf nodes. So let me be clear. 3 is the value and it is a leaf node and it is E. 5 is the value of this leaf node and it is A. 7 is the value of this leaf node and it is C. 9 is the value of this leaf node, it is B. 10 is the value of this leaf node, it is F. And 15 is the value of this leaf node and it is D. Why did I specifically mention these are leaf nodes? You have to understand these are independent leaf nodes as of now. And then I put all of those into a min heap. Okay. I am extracting two of the smallest nodes from it. So I got one node which is 3, which is having E, and other node which is having value 5. This is the node corresponding to A. What should I do now? I have to create a new parent node. New parent node will be having frequency as the sum of frequencies of these two. So 5 plus 3 is 8. 8 is the frequency and its left child should be the smaller one. That is, whichever you picked initially from the heap will be smaller. That is my left child. So 3 is the value and it corresponds to E. And which is the right child? The second pick, which is 5, corresponds to A. This is my new node. So I no more have E and A as separate nodes. The new node is this subtree. Okay. This node I am going to insert back into this min heap. So now I don't have E and A. Instead of that, I am going to put this back. I am having 8. 8 is having 3 as the left child and 5 as the right child. So it corresponds to E and A. This is my present min heap. So I understand the order is slightly disturbed, but just understand that all these nodes are present in the min heap. What is the next step? I have to find two of the smallest. Which are the smallest? See, you should not count 3 and 5 now because the node inserted is having value 8. Only the parent node is inserted, right? So parent node is inserted, which means it automatically includes the other two nodes, but you are not considering the other two nodes for any further calculation. Inside the min heap, you are only inserting the parent. That is what I explained initially, that min heap will be represented by array. Into this array, you will be putting the address of this parent. So that parent automatically have links to the children. Okay, that is how it is. You are taking the smallest two again. Smallest one is having value 7, which corresponds to C. It is this. And second smallest is what you just inserted, which is having value 8. So 8 is also taken out. 8 is having left child 3 and right child 5 already. And they are corresponding to E and A. What happens now? I have to merge these two into a new node which is having frequency as the sum of these. So 7 plus 8 is 15. I have a new node which is having value 15. And what is the left child? Whichever I took initially, that is having value 7, corresponds to C. What is the right child? Right child is this subtree as it is. So 8 is my right child. 8 is already having a left child which is 3 and a right child which is 5. So these are E and A. So this is my new subtree, and previous two entries, this as well as C, will no more be present in the min heap. So instead of that, min heap will be substituted with the new one which is 15. Then it has 7 as the left child which is C. On the right child it has 8 which is having 3 and 5 which are corresponding to E and A. What is the next step? Next step is I have to pick the next smallest two from this min heap. In this min heap, which are the smallest two? B and F, which are having 9 and 10. Those are the smallest two. What will I do? I will first take B out. 9 is the frequency, it corresponds to B. 10 is the frequency of the second one, which corresponds to F. So I am taking these two out of the min heap. What should I do? I should again add these frequencies. 19 is the value of the new node. It has left child having value 9, which corresponds to B. Right child is having value 10, which corresponds to F. So this is my new node, and I am adding this back into my min heap. So when I add it back into min heap, what happens? 19. It is having left child with value 9, which corresponds to B. Right child with value 10, which corresponds to F, right? Again, I have to repeat the same process. I have to take two of the smallest. Which are the smallest here? This subtree is having 15 as the frequency. D is also having 15 as the frequency. So I'll take out these two. So this subtree I'm going to take out. It is having 15 as the frequency. So 15 and 15, when I'm not writing both those here because it is a larger subtree, it will simply consume time. Let us just draw the new subtree which is having the parent. Okay, in the parent, 15 and 15 when added should be 30, should be the frequency of the new parent node. What should be the left child of this parent node? The left child of this particular parent node which is having 30, it should have this particular complete subtree. So it is 15. 15 is having another child 7. 7 and 8 is the right child. So I'm copying it from here. Okay. And 8 is having left child 3, right child 5, and 7 corresponds to C, 3 corresponds to E, and 5 corresponds to A, right? And what is the right child of 30? Whichever is the second smallest. So this was the smallest. This is the second smallest. See, both are having the same value 15, but I'm assuming that when I took it from the min heap, the left one, this subtree came first, and then this node having value D came second. That is why I'm considering D on the right side. Okay. So this is having value 15 and it is node D. So now these two are now no more available in this min heap. And what should I do? I should substitute it with this complete subtree. So if I have this subtree here, 30 will be the parent. There is 15. This 15 is another having a left child, which is having 7, which corresponds to C. And there is a right child, 15, which corresponds to D. This 15 has a right child with value 8. 8 has a left child with value 3, which corresponds to E. And 8 has a right child with value 5, which corresponds to A. Right? So these are the two subtrees presently present. So at this point in min heap, how many nodes are part of the heap? Part of the heap are only two nodes. One is having value 30, one is having value 19. So this is the most important point you have to keep in mind. All these nodes are not part of the min heap. Part of min heap is only the root of each of these subtrees, right? The remaining subtree is part of that, but not part of the min heap. In min heap, you only have two entries inserted at this point. So you are taking both those entries out now, 30 and 19, which is the smaller. 19 came first and then 30, which means 19 should be the left child, 30 should be the right child. What should be the parent node now? 30 plus 19 will be 49. So the frequency of parent will be 49. And what about the left child? Left child will be having value 19. So left child has frequency 19. 19 is the frequency of left child. 19 has a left child with frequency 9 and a right child with frequency 10. This 9 corresponds to B, 10 corresponds to F. What about the right child of 49? 49 has this complete subtree as the right child. 30 has a left child 15. 30 has a left child 15. So I'm just copying this part, okay? And a right child, which is also 15. And the 15 right child corresponds to D. You're understanding, right? I'm just copying this subtree as it is. This 15 has a left child 7 and a right child 8. What about 8? 8 is having a left child with value 3, which corresponds to E, and it has a right child with value 5, which corresponds to A. So I am going to remove this. These both are already removed from the min heap, and I will directly add this tree into the min heap. This is what finally happens. So at this point, only one node is there in the min heap, and that one node is 49. So whenever you have only one node in min heap, you can stop this process. You already have the Huffman tree ready. So once you have the Huffman tree ready, how do you identify which are the different Huffman codes? In order to identify the codes, the first thing you have to put zeros and ones. So you put 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. And what are the codes now? What is the code corresponding to A right now? A is here. So because A is here, you have to start traversing from the root and you have to go till A. So 1. After 1, you reach 30. From 30, you take 0 to reach 15. From here, you take 1 to reach 8. From 8, you again take 1 to reach 5, which is of the value A. So 1011 is the Huffman code for A. What about B? B is present here. So to reach from 49, which is the root, you have to travel 0, 0. So 0, 0 is the code for B. What about C? For C, C is present. Where is C present in this? C is this. Okay. So C is 1, 0, 0. So 1, 0, 0 is the code for C. What about D? D is present here. 1, 1 is the code for D. So I'm just coming from root till this point. What about E? E is present here in the bottom. What is the code for it? 1, 0, 1, 0. So 1, 0, 1, 0 is the code for E. And what about F? F is present here. So 0, 1 is the code for F. 0, 1 is the code for F. How do you calculate the total cost now? A is consuming 4 bits. So 4 times A's frequency is 5. 4 into 5 means 20 is the total cost associated with A. What about B? B is having 2 bits and it is occurring 9 times. So 2 into 9, 18 is the total cost associated with B. What about C? C is having 3 bits. It is occurring 7 times. So 7 into 3, 21 is the total cost associated with C. What about D? D is taking 2 bits and it is occurring 15 times, which means 2 into 15, 30 is the total cost associated with D. What about E? E is having 4 bits and it is having 3 occurrences. So total 4 into 3, 12 is total number of occurrences of total cost of E. What is the total cost of F? F is taking up 2 bits and it is occurring 10 times, which means 20 is the total cost associated with F. So the next thing is, if you add all these, you will get the total cost of transmitting this complete message, which is having 10 A's, 9 B's, 7 C's, 15 D's, 3 E's and 10 F's from one point to other. So what is the total total cost? Means total bits. That's what you're counting. Okay, so what is the total cost? 20 plus 18 is 30, 38. From 38 you have again 21, which is 59. Then you have 30, which makes it 89. Then you have 12, which makes it 101. And again 20, which will be 121. So this will be the total cost in this particular case. So this is how you prepare Huffman codes in order to transfer message. This is a lossless data compression technique which helps you to transfer data from one point to the other without losing any data. So this is how you will encode from English to binary using Huffman codes.